Okay, so yeah, thank you for inviting me to present on some storage research we have done in, or we are doing in the HAB-CCE project. So I'm presenting on behalf of the HAB-CCE project, in particular of the storage optimization group. So the High Energy Physics Center of Computational Excellence, HAB-CCE, has been presented before. So I will only give a very brief introduction of what we are. So we started as a 3-year pilot program from 2020 to 2023. COVID kind of upsets the counting of years a little bit, but we had a pilot program. And then in last summer, we had a review, and now we turned into a base program. It's a US program targeting 6 experiments, mainly from the energy intensity and also from the cosmic frontiers. However, I will concentrate here, focus on energy and intensity frontier. There were 4 and now are 5 US national labs participating: Argonne, Brookhaven, Fermilab, and Berkeley. And with the base program, Oak Ridge joined us as well as a 5th lab. Within the pilot project, so the 3 years from 2020 to 2023, HAB-CCE really concentrated on one major issue, and that was our goal to deploy the US leadership computing facilities to help future HAB computing challenges, such as in particular processing cycles. We all have seen the plots where we show the needs for processing cycles, computing for high luminosity LHC, and even also for Dune, being far beyond what traditional grid computing can provide at an affordable cost. And the idea was, since we have those leadership computing facilities to utilize, and they have lots of computing cycle, to utilize these for HEP computing. There are lots of challenges. They were addressed in different threads. There's a portable parallelization strategy group which has addressed the offloading to GPU and has reported here before, so I will not go into that. And then there was a fine-grained I/O and storage on HPC group. That's the group which later formed into the storage optimization group. And in the pilot project, we focused on making I/O of HEP workflows work on these high-performance computers. We had 2 major projects which we completed. One is we demonstrated the capability of leveraging parallel I/O libraries to write HEP data into more high-performance computing native backends, in particular HDF5. And there was a presentation which I linked here. And that's, of course, important that when we execute our workflows on an HPC, that we can do I/O in a manner that is maybe more efficient to an HPC. And HDF5 is often more familiar to HPC experts and kind of removes a potential hurdle of interactions. Another important aspect is to be able to characterize and monitor our I/O interaction on an HPC, which can be very different from what we do on the grid. And there was an existing tool which was called Darshan, and we enhanced that tool to make it usable for our HEP workflows, and we did monitor HEP workflows from Atlas, CMS, and Dune. And there was a presentation here too, and again, I put in the link. And I will have just a short summary on the next 2 slides about this. So when we enabled writing of data to HDF5, we did not try to produce a full persistence backend. Our idea was to have intermediate data stored in HDF5. So data that the workflow on an HPC would write and then a later step would read. We have those workflows in Atlas and also in CMS and I think in Dune. So our approach was because HDF5 does not have an as comprehensive data model support as root, to use root to serialize our complex data, potentially complex data models into byte streams and then store these blobs into HDF5 or really than any other data format. We can do that relying on root serialization to support our data model. We can either do that serializing data products by themselves and then appending them to larger objects and put those into HDF5, or we can collect them by event. And we studied that, and as I said, there was a chat presentation about that. On the Darshan, so Darshan is a tool that allows us to monitor I/O interaction of our workflows. And we have done that for, I show here Atlas and CMS, and we looked at our various steps of our production workflows. And they have different input-output needs, generation, simulation, reconstruction. They all have different output needs. And one of the workflow steps that is in particular I/O intense is filtering, the derivation of physics data. Often you have already your reconstructed quantities, and now you just filter out what's needed for many analyses. So it's often a very I/O intense process because you don't do a lot of processing. And Atlas has used Athena multiprocessing, a multiprocessing workflow for that. So this was kind of interesting because we have something which we called a shared writer, and we pass the data to be written only by that single process, so we don't have to merge any files. And Darshan, the tool which was developed by HPC experts, clearly showed how the read and writes are different for the workers that process the events and read them, and then what we call the shared writer that collects the data and is really the only process, you see the orange here, that writes to the disk. So Darshan really became a very helpful tool, which also was adapted into the Atlas repository so that we can use it besides CCE studies. Okay, so that was really the pilot project. As I mentioned, in summer last year, we then had a Department of Energy review of that project, and that found our work, the work of the pilot project, to be very helpful, and it was a successful review. And HAPCCE evolved into a base program. I now call it HAPCCE2, and somewhat expanded its scope. In particular, for the I/O group, it became now a storage optimization. So that means we were no longer just tackling the CPU problem by trying to port workflows to HPCs, but we are also looking at the other compute challenges that come with high luminosity LHC. In particular, the storage needs. So on the right-hand side here, you see a plot from Atlas. There's a similar plot from CMS, where our predicted disk storage needs in this case are larger than what we can expect by just technology improvement, unless we do some very aggressive R&D. And that R&D may actually be very similar between Atlas, CMS, and Dune. There might be approaches that help both of them, or for sure there are, and it is beneficial to do that kind of research together and then carry it to the experiments. Also, some of relevant service research has been done by computing scientists already, and we have computing scientists as part of HAPCCE as well, and we can benefit from their research. It does not all need to happen in high energy physics itself. So we don't want to have storage research resources become a limit on our physics research. So we have to get down to that red line, at least, or even lower than that, because if budgets are bad, we want to be really below that lower black curve. So we want to make sure that we use the storage as best as we can. So we optimize data storage and data management, and we have a few new topics investigating new storage backends and data reduction. One is something I will focus on today too, and I also know that Vincenzo, of course, will cover that, is tracking and aiding the evolution of root I/O, in particular ntuple. ntuple will be a major new development. I will show that later. And of course, Vincenzo will show that, of which the experiments are expected to take advantage. Some of the challenges in the migration will be common, so we want to help that migration and enable the use of our ntuple. Reduced precision and intelligent domain-specific compression algorithm has been used in many sciences, not so much in high-energy physics for good reasons. However, with the data volume ever increasing, it may be a point in time where we want to revisit that and find areas where we can use intelligent compression. Object stores is a new computing technology that allows us more strategies for data placement and deduplication. And then lastly, but not least, the data, if you want to process something on an HPC, has to be delivered to that HPC. So we have to think about how can we do that in an optimal way. Okay, next slide. Okay, so maybe my focus is the first bullet. So root is developing a new data container to replace T3. Root is moving from T3 to our ntuple. So obviously, root has been the HEP community software for decades now, used from data processing to physics analysis. It's really a community ecosystem. And T3 has served many experiments as a storage backends, enabling us to use the root ecosystem. It's a primary storage backend and I/O subroutines for many HEP experiments for decades. I remember POR, but I remember the switch, and that was very early in my career. So many on the call probably have only worked with root. Over the time, over exabytes probably of data are stored in T3, showing how successful T3 really was or is. T3 at the same time has evolved to address many of the HEP experimental needs and has been the backbone of our computational workflows. So now T3 supports the persistence and I/O of our complex experimental data, and it's really outstanding there. It's often only T3 supporting the complex C++ features we have. So that's related to what I mentioned earlier, that HDF5, that's much harder to do, and we choose root to serialize because root comes with this strong data model support that's really exceptional. However, T3 architecture predates many of the recent overhauls in C++, many modern programming paradigms and evolving computational landscapes. It is over 2 decades old. It is a generation old, and there's almost only so much you can do without really breaking a concept to evolve a concept. And the root team has found it is time to do a more substantial break and go from T3 to our ntuple. So on the timescale of high luminosity LHC, the root will deliver a new storage backend called rntuple, which will be part of root version 7. I will not go into the technical details on how rntuple works. That's not our job. That's what the root team does, and I'm sure Vincenzo will have more details here. It will be the state-of-the-art app community supported storage and I/O system. So it will be as relevant for high energy physics in general as T3 has been over the last 2 to 3 decades. It will address storage and I/O requirements for upcoming HEP experiments, but it also, to do that, it will have a streamlined compared to T3 data model support, more limited data model support. That will allow Atlas and CMS first glances to save about 20 to 40% of their storage. Again, there was a CHEP paper on that, which I linked here. But just let me point out that the 20 to 40% savings in storage for Atlas and CMS, again, represents exabyte of data. So T3 success is having stored exabytes of data. Ntuple's success will be saving us exabytes of data in storage. It uses a more modern C++ approach because it is developed on a more recent timeline. That includes adoption of smart pointer, better error handle mechanisms, and more modern C++ libraries. Again, Vincenzo will have some details here. For us, the important point is HEP experiments will have to adapt to rntuple, not just to take advantage of those substantial savings and the performance increasements, but also to stay current with root. And root, again, is our HEP software ecosystem. So even experiments that do not need the performance increase that rntuple delivers may want to adopt rntuple just to have the latest storage container of root rather than being tied to a T3 that was developed in the last generation and will only be maintained to remain functional. That means that we have to use the new rntuple API for our frameworks, and that we may have to change our data model to be persistent-viable in rntuple, as I said, which has limited data model support. And here's something CCE can help with to find common approaches to do this. So this is the topic of tracking and aiding the evolution of root and rntuple. So we want to aid the HEP experiments to adopt rntuple. And when I say HEP experiments, that means in particular Atlas, CMS, and Dune participate in CCE, but not only. We will also document our work and invite other experiments to participate if they want, so they can take advantage of it. Together with the root team, we had co-organized an rntuple workshop at CERN in November. I give the link here. And as an outcome of that, HAPCC is currently conducting an rntuple API review since the experiments need to use that API. The root team approached us to have a kind of experiment common review. We kicked that off in February. We had a first topical meeting last week. So we are going through that. We are hoping on a timescale of 3 to 6 months to give feedback to the root team on how the experiments feel that their current rntuple API fits their need. We want to aid the development of rntuple itself as by the requirement of the experiment. So we will analyze the requirements of the experiments, combine them where appropriate, and feed that back to root so that root experts can have one set of requirements rather than competing requirements between Atlas and CMS. On the other side, we will also find guidelines and recipes for the experiments frameworks and data models to be able to migrate to RNtuple. RNtuple is not foreseen to be a plug-in T3 replacement. There will be code changes for the experiment frameworks. Some of them may be helped by common recipes. The review and HAPCC in general includes experts from Atlas, CMS, and Dune. Experiments, other experiments are welcome to join everything CCE does is open and very welcoming. Plus, we have computer scientists from our computing divisions at the national labs here, root experts, and we are open to everyone. So, RNtuple, what is the current status of the experiments and their frameworks? So Atlas with Athena, Atlas reached a major milestone some time ago. We currently can store all of our production event data in RNtuple. There was a ACAT paper on that which I linked, which documents that. So that's really a major milestone. And that was helped by the fact that our framework encapsulates the persistent technology, the T3, which currently writes to T3. So the changes had to be minimal there. And we also separate our complex event data model from persistence, something we call TP persistence. TP separation. So T3 never saw the most complex parts of our event data model. So it was easier to put that to RNtuple. For CMS, CMS-SW is capable of storing analysis, nano AOD in RNtuple. I'm not the expert here, but it has been able to do that for a while. There is work on the way to be able to store their mini AOD and other data products in RNtuple. The challenge here is they use some currently unsupported features in their data models, features that are not supported in RNtuple. They are supported in T3. For example, dynamic polymorphism. So they consider storing the data in unsplit mode in RNtuple, which is something which RNtuple recently added. So they are making progress. Dune and Art, I don't think there have been significant studies with Art and RNtuple yet. They hope to benefit from some of the CMS-SW developments because Art is only a clone from CMS-SW some time ago. So there may be some commonalities, but there has been nothing specific to Art. HAPCCE, however, has done some work with Dune's analysis format data to store that in RNtuple. And there too was a ACAT presentation, and I give the link here. I will show both of those ACAT presentations just in the following slides. Some more overview. Experiments that are not really part of HAPCCE, but I want to present them here too, are Alice and LHDB. The Alice data model is built on arrow tables, so that's not very complex and should be storable in RNtuple. Alice relies on bulk reading, which is something that should be done in RNtuple, so I don't think there are major hurdles for them to move to RNtuple. Similarly, I think for LHDB, which uses a rather flat ntuple, again, that's simple, so that should not be a big challenge for RNtuple to store. They do require multi-threaded I/O, which has been implemented in RNtuple, but there may be testing they need to do to really find out whether it scales well and so on. Okay, going back to Atlas and Athena and RNtuple. Sohan gave a very nice presentation during ACAT, summarizing the status of the Atlas experiment RNtuple. And again, Atlas can now store all our production data formats in RNtuple. we can read and write that. However, we cannot read and write that necessarily in our production workflows yet. Some of our production workflows are either multi-process or multi-threaded, and we have not fully tested n-tuple reading, writing in multi-process or multi-threaded versions. However, we see Atlas sees about 20% storage savings, especially in our analysis formats, where it may also be most relevant. There's still a lot of work to do. Just being able to store your data in n-tuple does not mean you're done. There are many production tools that need to be ported to n-tuple. So Atlas uses things like fast merging that currently works only for T-trees, so where we have to do developments with n-tuple, and those developments are in progress. Also, there are always standalone tools that can depend on T3 and they need to be ported. So just being able to write data to n-tuple does not mean that you're done, but it is a major accomplishment, and we will finish up the rest probably before long shutdown 3 and test them during shutdown 3. For CAF data, so Amit did some work here, and making sure that CAF data, the standard record here, can be persistified in n-tuple. He too saw substantial storage savings for that. Dune uses CAF for the analysis data, and you can find his ACAT presentation in the previous link. Okay, that's really all I wanted to say about our n-tuple topic. Little bit less time spending on the other issues we are focusing on. One is reduced precision and intelligent domain-specific compression algorithms. As I pointed out, most of our data we store only using lossless compression. Lossy compression is far less common. There are a few pockets where we do that, either in a single domain, well controlled, or in some of our data products, but it's less common than lossless compression. So as storage needs go up, maybe we want to revisit lossy compression, and in particular, some of the intelligent algorithms that our computer science counterpart authored. I'm not talking about lossy compression or intelligent compression for raw data. However, our derived data may be more suitable data. We won't touch raw. Nobody wants to lose precision in our raw data, but lots of our data which we store on disk is actually derived data that in principle could be redone. One of the hurdles is not that there are not algorithms that can lossy compress your data and save you lots of storage. The problem is that we need trust building and safeguarding validators. Often, especially for multi-purpose experiments, the fear is that you lossy compress your data and thereby impact the physics that is done on that. And that's a high challenge, especially for multi-purpose experiments, because you don't exactly know what's done to our light data or CMS's nano ADUBs, because there are hundreds of analyses done on that. So we need to build those trust building and safeguarding validators to make lossy compression more acceptable. In our previous incarnation in the pilot project, we actually had started with looking at some of these tools developed by computer scientists. So there are different lossy compression algorithms. I list them here, MGuard, SC, and IdeaLAM, that could help us minimizing the storage footprint of some of our data. So we are in the process in storage optimization now, we are in the process of developing a compression test framework that allows us to generate or take as an input some data and then apply these lossy compression algorithm to them and store them in our HEP storage container, so including our tuple. Then we can perform tests and in particular measure the fidelity and usability of that compressed data downstream and see whether it's still usable. Again, we won't do anything to the raw data. We are just taking pieces out of the raw data, which we then compress and feed it downstream. Raw data itself will remain lossless forever. A particular example here might be the Dune far detector trigger raw data, which has large waveforms in them. They have gigabytes of frameworks, gigabytes of storage, and that can't therefore be copied into downstream data products. However, it may be that if you intelligently compress that it becomes so small then that you can do a copy of those smaller waveforms into your downstream data. That then could enable analyses to use the derived data rather than having to go back to the raw data, and could make the computing workflows much easier. So Amit has done some work here. So there is a representation of a waveform and then persistified in our tuple. You see the data here, you see the size on storage, that's 1.1 megabyte. And if he uses intelligent compression for that, set size is reduced by a factor of almost 100. That reduction depends on settings also, but the point here is really we can do the workflow, and lossy compression can result in a large storage footprint reduction. One could easily imagine that there are many scenarios where you don't want to have an extra megabyte in your data, but an extra 12 kilobyte is very manageable, so that would allow you to add this to downstream products. We still need to do testing on the fidelity of that data, whether something compressed by a factor 100 could be useful. Other sciences do use these compression algorithms, so there is merit to that being used. Okay. Shifting gears again to object stores and strategies for data placement. So using object stores and breaking out of file boundaries by itself does not save storage. However, it may give us means to deduplicate our data. And in particular, there are 3 ways where on how that could happen that I want to point out here. So having broken file boundaries, we may be able to reference upstream data rather than having to copy it into a downstream data product, because then you can navigate to that reference. You don't need to navigate across file. It also may allow finer grained versioning. So when you produce your data and you find you want to update one particular container, let's say the photons, then you can do that without having to rewrite all the other data that didn't change, the electrons and pions and whatever. So there again, you would write only the changed data and reference the unchanged data, and thereby avoiding duplication. Another example is the experiments often have a common analysis format. However, some analyses may need extra data for some of the events, for subset of event, and breaking out of file boundaries may allow you to write these augmentation for just the events where they are of interest, and again reference to them to the common part rather than having to duplicate the common part. So by deduplication allowed by object store technologies, these methods may actually save substantial storage space. So there is a lot of object storage, store activities on the high-performance computing side. For example, DEOS, distributed asynchronous object storage, is developed here too at Argonne, at the Argonne Leadership Computing Facilities. It uses persistent memory technologies for very high performance, has a data model that is key value based, and it can be accessed either via POSIX or directly via custom API. And DEOS is of particular interest to us, maybe, because DEOS is also supported by root rn-tuple. Root rn-tuple, one of the new features that rn-tuple will come with, is support for DEOS. So HAPCCE has a group studying object stores, and in particular DEOS implementation of rn-tuple, and we do that in a similar way as we had studied I/O and HPCs before. We provide tools such as Darshan to be able to augment rn-tuple DEOS implementation and see how our I/O behavior on HPCs with DEOS works. That gets me to the outlook. So we have become, HAPCCE has become a base program. So therefore we now can contribute a little bit more, a little bit wider variety of challenges, including storage. We are not limited by only porting things to high performance computing, which is an important aspect, but wouldn't solve our storage challenge. And now we can contribute to solutions that helps the storage challenge. However, we need to ensure that we are relevant to our clients. Our clients are the experiments. Therefore, we are open for a contribution from everyone. We are always open for dialogue, and please feel free to approach us if you have special needs or want anything where HAPCCE can help you with. Experiments currently represented in HAPCCE are CMS, Dune, and Atlas. And we also work together with computing scientists from the computing divisions of the lab, and with community software experts such as Root. We have them either as part of HAPCCE or we closely work with the Root team. That's it from my side. Thank you very much for listening. Any questions?
Well, thank you very much, Peter, for a very nice overview of some interesting work. So yes, we have a question. So Douglas?
Yeah, there's two questions. Peter, can you go to slide 5? Please.
I'm doing. Yes.
Last bullet, optimize data delivery for HPC systems. Is that using what already exists, or is that developing something new?
So, Doug, that was mainly geared to help with a Dune use case. So Dune stores some of their data, the raw data and other data, in HDF5. And they wanted to have HDF5 streaming, or they need HDF5 streaming.
Okay, that's what you mean by that. Okay.
Yes, yes. So that's part of it. At some point we had hoped, and it may still happen, to have a 6th lab become a part of HAPCCE, which has a lot of expertise in that area. That hasn't happened yet. So this is lacking behind a little bit, but...
Okay. Can you go to slide 17?
That's my
16, I'm sorry.
Yes.
Any idea if we'll use object stores more? I mean, what's the penetration in across the DOE? I'm specifically talking about DOE because I'm a U.S. person, of course. Is using Deos for object stores? Are all the HPCs using that technology or just one?
So I think currently it's just one, but Doug, you're much more the expert here than I am. So I should mention that one of the HAPCC experts working on this is actually Doug, and he's asking me questions right now. So,
No,
so
the reason I'm asking is because in grid space for object stores, we use
yeah,
stuff based off of Ceph.
yes,
I don't know. We will have to talk to the NERSC folks to
yes,
see what their plans are for
yeah,
NERSC
yeah,
10.
yeah. So I think there is nothing that limits us to Deos. We have a lot of Deos expertise on the computational side, and there is one HPC that comes with Deos. Deos is implemented in our ntuple, but that does not mean that we are limited to Deos. CMS has done studies with Ceph, which they presented. I see Nick raised his hand. Nick actually presented that in our iOS group. So it's not limited to Deos. I think I want to go to the next slide there and highlight the second bullet I made there. It really depends on what's relevant to the experiments. So if experts like Nick and Doug feel that Ceph is more relevant to the experiments than Deos, then we can do studies with Ceph as well. Does that make sense?
I don't know, Nick, do you have a related question? Is it a follow-up or is it a separate question?
It's related, yeah.
Okay, sorry, Doug, have we covered your questions and Peter? Then we can go on to Nick.
Completely. Yeah, completely.
Yeah, okay, then yeah, Nick, please go ahead.
Yeah, maybe on 15. Yeah, I mean, just to, highlight what Doug already pointed out, a lot of these advantages we're talking about in this first main bullet here,
Yeah.
they're to save on storage costs, right? Whereas Deos is a very high performance storage technology and therefore very expensive, right?
Yeah.
So that's sort of the motivation here is to hit these bullets with regards to, saving space and making analysis more flexible. We're really interested in low cost S3 like storage technologies, and then investigating. The challenge here will be managing the metadata and tracking these objects. I think building a system that can track all of that. I just wanted to highlight that. Thanks.
Yeah, I think that's a very good point. Yes, and I think that's definitely true. Let me point out that this first bullet here, those techniques are really independent on independent of the object store implementation, on whether it's Ceph or Deos or some different. Those are techniques which are more the metadata handling of the data, the reference handling, and so on. And Nick had presented some work CMS has done, which mostly addressed, I think, the first two sub-bullets, Nick, if I'm not mistaken. Atlas has done some work along more of the third bullet. And I think all three of them actually can be techniques that can be implemented with object store, and that does not mean to be Deos.
Yeah, I would agree.
Yeah, thank you.
Okay, any more questions for Peter? No, okay, well, thank you again, Peter.
Yes,
and we move on to Vincenzo, who will tell us more about our ntuple.
Hello, can you hear me?
Your volume's a little bit low.
Yes, let me try to increase. How about it now?
That's better, yep.
All right, perfect. Now let me share my screen. It should be this one. You can see the slides, I guess.
Yep, that's good.
Right. Okay, let me now just remove the zoom in.
Yeah, sorry, I think maybe if you could just go a little bit higher on the volume.
Yep, yeah. Okay.
That's good, thanks.
Yeah, perfect. Thanks for the invitation. as Ben already said, I will now introduce a bit more the details of the Arentapo design, and then also a bit of a dive into the support for object stores. So the main topics are the design and the support for object stores. But clearly, let me start with the motivation for developing this new tool. So clearly, we have a lot of challenges ahead of us. One of them is the increase in dataset size for high luminosity and future experiments. But the other one is the exploitation of the modern hardware. Which clearly has come a long way since the initial period when T3 was developed. So just to give a rough calculation here, at 10 gigabytes per second, we have roughly 3 microseconds to process a 32 kilobyte block. So now we need many more optimizations in the I/O stack than before. These include, for example, being natively parallel and asynchronous in the I/O requests, and also eventually supporting heterogeneous hardware. We'll see some of that later as well. So Arentapo, just to go through the brief introduction, is based on the 25 plus years of experience that T3 already provides. Clearly brings many more advantages than T3. Some of those that Peter already discussed in the previous presentation, such as less disk and CPU usage, while at the same time aiming at covering the use cases of experiments that use T3 already today. We have a binary format which is defined in a dedicated specification you can find online on our repository. And roughly on this slide, I just wanted to highlight roughly the timeline for Arentapo going into production as we imagine it today. So just a brief interlude about the Arentapo workshop that we organized in November. As Peter said, this was a co-organized together with FCCE. And here we had one presentation by each experiment about their current understanding of the Arentapo tool and the adoption or the level of adoption that they present today, as well as some other presentations which were more related to utilities and other types of features that might be useful in the context of a storage system. One of the nice outcomes of this workshop was a revisit of the program of work for Arentapo, targeting a first production release by the end of 2024. So this was done clearly in conjunction with the experiment requirements. And here in this slide, I wanted to present the latest, our current understanding of the schedule for Arentapo. Keep in mind that this was presented initially in 2021, and today is the current status of it. And you can see that most of the original goals were met, which is already a good sign. But the goals that are now remaining towards the production use cases, especially those that are highlighted in violet, those are goals that require also a lot of exposure and coordination with the rest of the community. So the more we go into the production stage, the more we see how Arentapo becomes relevant also in various use cases together with community experts. So now a brief introduction about the inner workings of Arentapo. I wanted to start by the data layout. If you have seen other presentations of Arentapo, you may already know about this, but roughly speaking, this is how your event objects are stored inside of an Arentapo. The beginning of the Arentapo features an anchor and a header. And then the end of the Arentapo has the information regarding where the actual data is stored inside of the data set itself. And then in between you have the actual data, which is divided into pages. So page is the smallest unit, smallest grouping of data elements. And you can see with the color coding in this slide that, for example, the floats of this particular struct are grouped here. Multiple pages are grouped together in this concept of a page group. And then roughly we are imagining that every page is in the neighborhood of 100 kilobytes, and then groups of pages can be collected together in a cluster. A cluster is practically identical to the same meaning of a cluster in a T-tree, which is usually also one of the units that we use for independent reading of different fields and different groups of rows of events. Finally, in Arentaple, there's also the superset of a cluster. It's a cluster group, and we are imagining that every cluster group will be in the neighborhood of 100 gigabytes. And all of this is still within the same file or within the same Arentaple object. And this is also done in order to reflect the future trend of having bigger and bigger data sets. If you're wondering about the read pattern, whenever you open a file, we need to once read the initial parts of the Arentaple in order to get information about the schema of the data set. And then once per cluster group, we need to read one of these lists of pages, which is just the information in order to know where the actual contents of the dataset are. And then Arentaple features a native asynchronous I/O. So there's a background thread which reads ahead page groups for the following clusters, so that this is already taken care in the background and actually helps a lot in reading contexts. So Arentaple introduces a new binary format. I won't go into too many details, but this slide, it was just to represent some of the things that allow for further optimizations, such as the more efficient storage of collections and Boolean values inside of the Arentaple. On the right side here, you can see an Arentaple object being stored inside of a T file, but Arentaple itself is independent of T file. So this is just one way to show it. We are also aware of some of the limits. These are the theoretical limits known for an Arentaple dataset to this day. I left this slide for reference, but the aim here is to clearly be prepared for next generation datasets. So most of these limits will be very large for today's standards. Clearly, on top of this, Arentaple also depends on the storage backend that actually concretely stores the Arentaple. So it can be on disk, or as we will see later, in an object store, but that's clearly orthogonal with respect to the values in this slide. Together with the main Arentaple infrastructure come a lot of utilities, and here I wanted to highlight a couple. For example, you can convert existing T-tree datasets into Arentaple through the Arentaple importer, or you can inspect the information that is currently available from an Arentaple file through the Arentaple inspector. And this can be detailed information about, for example, the compression level and how many bytes are stored in each field and each column of your Arentaple. Other than that, clearly you have read and write metrics, which is akin to T-tree perf stats, and those can be enabled when either writing or reading an Arentaple object. So now I wanted to give a quick look about the performance measurements that we have seen so far. It's clear from our numbers that Arentaple brings performance improvements across the board. Something that was mentioned by Peter already, but we have seen also not only improvements in performance, but in terms of storage savings as well. And I have a link here to this nice presentation by Serhan from the recent ACAD conference. RNTuple is tightly integrated with the rest of Root. So clearly you can use our data frame, so the data analysis interface of Root, to read RNTuple data. In this slide, I also wanted to highlight one of the other efforts that are ongoing for our data frame, which is also very much aligned with the concepts introduced by RNTuple, which is the bulk processing. And in this slide, to the right side, you can see that adding the bulk reading of RNTuple data and bulk processing of the events that are read in bulks from the data set, the wall time sees a nice decrease with respect to the equivalent T3. Clearly, RNTuple should be readable by our data frame, but one question there is also how complicated is it to set up a new analysis that runs with a new data set? And the answer is not complicated at all. I just wanted to highlight this in a recent example. So there's this analysis grand challenge, which is a benchmark for a realistic type of analysis for high energy physics. Currently, the benchmark is based on TT-bar analysis for reading CMS open data. We converted the original data set, which was clearly in T3 format in nanoEOD, to RNTuple. And the only difference required in the user application to repeat the analysis was just changing the string with the path to the dataset to the new path to the RNTuple dataset. Everything else, all the data frame calls and the rest of the program stays exactly the same. So the transition from analyzing T3s to analyzing RNTuple will be really seamless for final users. And then a final note about another set of benchmarks that were run with RNTuple, showing again a nice performance improvement with respect to T3. These are called ADL benchmarks, Analysis Description Language. You can find the repository there, and in this case you can see again another example of the performance improvements that RNTuple can bring. So as it was also mentioned in the previous presentation, RNTuple is currently under review by external experts. In this case, it's the FCCE collaboration that is taking charge of this review. We are very happy to have this kind of external validation, because this should help us assess all the functionalities and the features and the consistency of our API. So we will use the results of this review to guide further developments. And talking about this, I just wanted to give a brief highlight of what is the current API. So RNTuple features multiple layers of the I/O subsystem. In this slide, we begin by the bottom layer, which is the one that is closer to the actual final storage. So these are the classes responsible for actually writing or reading from disk or object store, depending on the backend. Then there's a layer which is responsible for grouping fundamental types like floats and ints into the pages that I was mentioning earlier, that make up the smallest unit of grouping in an RNTuple object. There's a higher level which maps these columns into their C++ types. These C++ types are most often what the user sees as the field, for example, a vector of floats. And this is the layer responsible for doing this mapping. And then finally, there's the high-level event iteration layer, which is what, for example, our data frame uses to access the contents of the RNTuple and then read them for further processing. In this case, as we have just discussed, there is the RNTuple object, and then the bottom layer is implemented in this rpage source and rpage sync classes, which represent reading and writing pages from the storage backend. And if you want to query metadata about the RNTuple itself, there is a class responsible for that, which is the RNTuple descriptor. Inside of the middle layer, so the layer that maps the C++ types to the fundamental types, you have our field. It's the central class that connects the in-memory representation of data to its on-disk representation, and then all of the connected classes up until the arrent-tuple reader and arrent-tuple writer, which are the classes responsible for the event iteration on the various fields. So now I wanted to move forward to the second part of the presentation, which is a bit of a detailed view into our support for object stores. So the motivation, as was already discussed previously, but in highly parallel settings, we align well, our requirements align well with the usage of object stores because they are much more scalable than traditional file-based systems, and especially they are widely deployed in cloud service providers. We see actually two types of targets here. On the one hand, you have HPC centers, and their technologies like Intel DAOs will be are already today or will be used commonly in the future. But then you also have all the cloud environment, and their other types of object stores like S3 or Microsoft Blob are more common. So in our case, we want to ensure that arrent-tuple can make use of every type of optimization, including the better scalability offered by the object store technology. So in this case, we need to find a way to map the data that is already available inside of an arrent-tuple into objects, because clearly that's the baseline for the object store technology. So that's the question, right? It depends on multiple factors. Do we want to store objects based on a cluster, based on a single page, on columns? Then we have to take into account factors like the throughput latency, and especially in cloud environments, the cost per request that is made to the endpoint. So I wanted to start with DEOS because this is the implementation for an object store that is already available today in arrent-tuple and has seen a lot of effort into improving its performance. We have also this plot down here, which is kind of a demonstration of the nice scaling in a DAOS cluster with native support for arrent-tuple data, and the mapping that is available so far divides the arrent-tuple based on clusters, and every cluster will become an object in the DAOS server. And then further down the implementation, you have different columns of the arrent-tuple, which are represented as DAOS D keys. And then you have the contents of the columns that are stored inside of this key as the values. So there's native support in arrent-tuple, and so far we've already demonstrated that it can scale. Clearly, this is one of the venues for further research, because the more experiments or other users will actually implement their workflows using data stored in such a system, and then the more we will be also able to improve on that. And then I wanted to also give an highlight of the current status of the effort for implementing the S3 backend. So in this case, Amazon S3 is widely available as the object store for cloud applications. It's a different use case with respect to DEOS. Clearly, in this case, you have more of a worldwide distributed storage as compared to the local fast storage system available in a single HPC center. So the network latency becomes noticeable, and also, as we said, the cost per request. So in the first implementation, there's a mapping of every arrent-tuple column to an S3 bucket. And there was a presentation last year that I left the link at the bottom of this slide. In this case, we see, so we demonstrated that the feature is working. So we were able to write and read arrent-tuple data to an S3 storage system. But we also see that there are inherent limitations with the current implementation with respect to the DEOS implementation. So this is pending further research. Maybe larger objects may mitigate the latency, but this is still to be understood a bit better on the arentaple side. So in conclusion, we are introducing and moving arentaple towards its first production version. We have clear deliverables set together with experiments, and we are also submitting arentaple for outside review, which will help us guide further developments before the first production version. arentaple enables this, so satisfying the storage requirements for next generation. In particular, object stores are becoming more available than before, and also analysis, final analysis can benefit from the integration with these other types of technologies. Very soon from now, we want to run petabyte scale testing with writing and reading arentaple data. This is something, it's an ongoing collaboration with the CERN IT department, and we'll see the results of that by the end of this year. Clearly finalizing the support for the V1 version according to experiment requirements is one of the main goals, and also introducing highly parallel writing, which might also enable more workflows than before for the production of HEP datasets in experiment contexts. And with that said, that was the end of my presentation. So thank you for listening, and if you have any questions, I will be glad to answer.
Well, thank you, Vincenzo. A very, very nice talk and overview again. Do we have any questions? Maybe then I just have one on the highly parallel writing, because it was also something I think that Peter mentioned in his about whether there's any advantage to going to a multi-process versus a multi-threading read-write. It's a naive question. I'm not an expert on storage, but I just wondered with the highly parallel whether there was it was better to do multi-processing, or whether multi-threading is still okay.
We're actually already have some effort ongoing on this side, and it's going to be a multi-threaded writer. And
okay.
So currently we are testing it internally in the team. We aim to produce some results in a few months from now, but the first implementation will be multi-threaded, and I expect this to also stay around afterwards. Yeah.
Okay, thanks. Okay, I think Vangelis, you were first.
Hi, thanks for this presentation. My question is more about the planning and timeline. Essentially, yeah, you mentioned that this year, I think you have a nice graph in the beginning, that you go towards production, and then you have the version of 1 of experiments requirements. So yeah, I want to understand better a little bit what is the timeline of if there is any kind of a freeze deadline that you have put there, and from the experiment side, that if there's a sort of a deadline we should reach in terms of helping with the developments and giving feedback on the format.
Thank you for the question. So this represents the feature set that we wanted to deliver. So the idea here is that V1 will represent a freeze of the binary format, so the on-disk representation of the arentaple dataset. This is just the first step towards actually giving experiments the stability and the consistency that they need to test this further in larger scale and production environments. Clearly, different versions so far, different release candidates of arentaple didn't pose any guarantee on the format and the binary representation and how arentaple stores things on disk, which is nice for benchmark purposes, but doesn't give the experiments the ability to actually put arentaple in their production pipelines. So we want to enable that, and that means that we need to have a freeze of the binary format representation. Then clearly there are and there will be many features that are not going to change the binary format, but that they will improve the arentaple storage system, and those can go also in future versions of arentaple.
Okay, yeah, this makes sense. And when this V1 freeze is going to happen?
So our current target is by the end of this year.
Okay, that's great. Thanks.
Thank you.
Okay, I think Douglas, you were next.
Slide 26, please.
Mm-hmm. Yes.
How many, we're since slide 25 and 26 show the use of our ntuple with two different object store technologies. Were there any changes you had to do in the code to get these similar results?
All right, I think I understand the question, and let me just go back to this slide, for example. So the implementation of how we write data into DEOS or S3 or any other storage backend is at the bottom of this hierarchy. Whereas the applications that read or write the arentaple data from the user side use this layer up here. So that means that practically user code was completely unchanged between the two implementations. What changes is the lower level of how we make the write or read requests to the storage backend.
Okay.
Does that answer, or?
Yeah, because I wonder if, for instance, Rob Gardner pointed out that some of the tier twos have object storage available now. It's the stuff that's typically Ceph based. And if it would make sense to sort of give you another local data point for object stores, because you're looking at two classes right now, one that's essentially distributed and may have wide area network implications. That's what you talk about for the latency.
Yeah.
Versus something that's within the site network, which is essentially DEOS.
Correct. Yeah, so if there's any interest in trying out or attempting an implementation for Ceph or just discussing how that could work out in principle, we would be happy to discuss it offline. This is one of the things that might not be part of V1, just saying. So
Yeah, of course.
I don't know if we'll have time to work on it this year, but at least knowing what's the perimeter around that could be already interesting now.
So that might be something that HepCC could help you with.
Okay, thanks. Yeah, maybe we can also further discuss this offline.
Okay, and then Ilya.
I see that you are now validating X3D accessing, and was wondering, are there any measurements already done when it comes to performance of wide area network? And the second thing is, is there any comparison on cacheability of arentuples compared to T3 content?
Okay, thank you for the questions. Let me try to start with the first. I believe what you mean is that you saw this slide in particular, and you saw the X3D path in the slide. Is that correct? Or
can you repeat?
So your question is whether arentaple supports reading data through the network via X3D protocol, and if we have any benchmark specifically about the performance of reading through the X3D protocol. Is that the first question?
Yeah, that would be first question. And
yeah. So about this, what you see in this slide is just an example of a certain application. Here, both data sets are stored on EOS, and we read them through X3D. But we don't read them. So the T-file plugin is the first point of access, and then RNTuple is able to request the objects through XRD this way. We haven't any particular benchmark that is focusing on the XRD performance of RNTuple versus T3 so far. So given that this benchmark was already run, showing the same analysis running T3 and RNTuple already provided better performance, I am going to say that even if we tried to isolate only the XRD read requests, we would probably still see better performance from RNTuple, deriving from the results that we already have, because we already have results that use files that were stored on EOS and we read them through XRD. It's true that we haven't done any, wide area XRD reading. So, for example, reading from in the US from CERN via XRD, and then maybe with some Xcache plugin, that hasn't been done yet for RNTuple specifically. That could be also clearly something nice to test, but I wouldn't expect that the results would change much.
All right, we will check. What about HTTP access?
Yes, same reasoning. You have HTTP through the T-file plugin, and then RNTuple can read data.
It has been validated. It should work.
Yes. But okay, yes.
Thank you.
What about the second question you had in the beginning?
So the other question was how well it yields to caching compared to T3 content.
Mm-hmm.
Because just the fact that you write it differently can change how much extra information you read and cache for each access.
Yes, this is an interesting question. So we definitely read less information that we had to read with T3, especially if you have a lot of collections. We have less metadata to read per event or per group of events. So I would say that should improve in that regard for caching matters.
I mean, it's more important really how it's ordered, because if you have the same branch, let's say, in with gaps in between for other branches, then your sparseness of read gonna be worse.
I understand.
But, I mean, it's something to be tested.
Yes.
By the way, why is footer placed at the end if it has to be read at the beginning?
It doesn't have to be read at the beginning. So the reading pattern. So in principle, you can only read the header to get the dataset schema, because you might only be interested in that. Imagine that you have multiple files and you want to just check that the different files have the same schema. That doesn't require reading through the whole file.
And because here read pattern says on file open that you read anchor, header, and footer.
Yes. Yeah. So, okay. So supposing that you want to read the whole file or actual data from the file, then you also read the footer, for example. Yes.
All right.
Also, maybe one comment on that topic. It's so the anchor, header, and footer are terminology. So where they are necessarily located in the file might not be what you see on this diagram. So in fact, right now what will happen is that header and footer will actually be written after all the pages. So they will actually in the T file be at the very end. And then only after that will be the anchor, which has to reference header and footer. So this is like header and footer are more terminology and conceptual terms here than actual location in the file.
All right.
Okay. Any more questions for Vincenzo? No. Okay, then I think we can close here. So thanks again to both Peter and Vincenzo for the very interesting talks.
Thank you.
And we will reconvene the next Computer Accelerate Forum on the 8th of May. So hope to see you all then. So have a great day, everyone, and we'll see you next time. So bye for now.